Okay, welcome back, students. Let's cover section 2.5. Section 2.5 is on Gaussian elimination. 2.5. Gaussian elimination. Okay. Named after Charles Friedrich Gauss, very famous mathematician. Okay, definition. The process of placing a system of equations. The process of placing a system of equations into an augmented matrix placing the matrix into row echelon form and then using back substitution to solve the system is called Gaussian elimination. Okay, number one, example one, use Gaussian elimination on the following system. Okay, so we have 4x1 minus 3x2 plus 6x3 is equal to 2. X1 minus 3x2 plus 6x3 is equal to 5, and negative 2x1 plus 3x2 minus 8x3 is equal to negative 6. Okay, so we're going to create a augmented matrix using the coefficients of the variables and then the constants that are on the right side of the equal sign. So our A pound, okay, or A number sign, I'm just going to call it a pound sign. Okay, our A pound is equal to 4, negative 3, 6, 2, 1, negative 3, 6, 5, negative 2, 3, negative 8, and negative 6. And I'm going to augment this matrix by putting a line between where I guess you would think that the equal sign would go, okay, between the coefficient portion of the matrix and the constant portion of the matrix. Okay. Okay, so let's use our elementary row operations to put this into row echelon form. Okay, so the first thing I notice is I have this 1, okay, right here. And so I'm going to want that 1 to be in the very first row. Okay, first row, first column, I want to be a 1. So I'm just going to permute those two rows, row 1 and 2. So permute row 1 and 2. And I'm going to get 1, negative 3, 6, 2, and then 4, negative 3, 6, oh, oops, that should be a 5. 5, and then a 2, and then a -2, 3, -8, -6. Okay. Okay. And then here's the augmentation on the matrix. I can make it a solid line or a dashed line, it doesn't really matter. Guess we'll stay with solid line. Okay. Okay. Next thing I want to do is I want to eliminate the 4. Let's go ahead and do that. Let's eliminate this 4. So we're gonna multiply row 2 by -4, or sorry, row 1 by -4, and then add that to row 2, replacing row 2. So that's going to be A1, 2 of -4. Let's multiply the top of that, the top row by -4, -4, 12, -24, and -20. Okay, now let's add these two rows together. Okay, and we will get okay, well, let's put in our first row first. 1, -3, 6, 5. Then that we're going to get 0. 12 minus 3 is 9. -24, 6 is -18. And -20 and 2 is also -18. That's kind of nice. Okay. And then the last row stays the same. It's -2, 3, -8, -6. And we'll put our line for our augmentation. Okay, now I want to get rid of this -2. So let's multiply row 1 by 2 and then add that to row 3. So this would be A1, 3, multiply row 1 by 2. So let's multiply that row 1 by 2. That's going to be 2, -6, 12, and 10. And then add that to row 3 this time. And we are going to get, first row stays the same, 1, -3, 6, 5. Second row stays the same, 0, 9, -18, and -18 stays that. And the third row, I'm going to get 0. -6 and 3 is -3. 12 and -8 is +4, and 10 and -6 is also +4. We're getting kind of repeated numbers here. Okay, so now we have some zeros. I'd like to get a 1, okay, along this diagonal. Remember this diagonal, we'd like to get some 1s there. So my next step might be to multiply row 2 through by 1/9. That'll get me a 9 in that middle row there. So let's do that. Okay, so if I multiply row 2 by 1/9, that is going to get me 1, -3, 6, 5, 0, 1. Whoops. It looks like a 65. It should be 6 and then 5. 1, -2, -2. Okay, and then 0, -3, 4, and 4. Okay, so now I'd like to get this guy. For row echelon, I just want a lower triangular matrix. So I just have to next work on getting this -3 to be 0. So how can I get that -3 to be 0? Well, I'm going to multiply row 2 by 3 and add it to row 3. Okay, so let's do that. Oops. We want A 2 3. Okay, multiply row 2 by 3 and then add it to row 3. So let's do that. That's going to get us 3, -6, and -6. Adding to row 3, we're going to end up with only row 3 is changed. So the first row is 1, -3, 6, 5, 0, 1, -2, -2, 0. The third row is going to be changed. That's going to be 0, 0. That's the desired 0 I want. And then -6, 4, that's -2. -6, 4, that is also a -2. Okay. Okay, the last thing that I want is this -2 to be a +1. So I'm just going to multiply row 3 through by -1/2. Okay, so multiply row 3 by -1/2. So m row 3 -1/2, and that's going to get me 1, -3, 6, 5, 0, 1, -2, -2, and then 0, 0, 1, 1. Okay, so now this is row echelon form. Okay, and I forgot to put my augmentation in. And so what does this tell me? Well, this tells me that I can rewrite these equations, my original equations, in what our resultant rows give us. Okay, so we created a coefficient matrix in the very beginning that represented the coefficients of our system of equations, and now we have a different coefficient matrix. It's a little bit more simplified, and we can use back substitution to actually get the values of our variables. So let's go ahead and do that. 1 times x1 is just x1, -3x2, 6, sorry, plus 6x3 equals 5. 0x1, okay, so there's no x1. I mean, I'll put it in for right now. 0x1 plus 1x2 minus 2x3 is equal to -2. And then 0x1 plus 0x2 plus 1, maybe I'll put the 1 here as well, plus 1x3 is equal to 1. Okay, so these 0 terms will go away. And so I'm really just left with, in the third equation here, the third one down, I'm really just left with 1x3 is equal to 1. 1x3 is equal to 1. Well, what does that mean? That means x3 had to be 1. Okay, and so now I can use this, okay, and plug it into the second equation and say, well, x2 minus 2x3s, well, what was x3? It was 1 is equal to -2. So now I can solve for x2. So this becomes x2 minus 2 is equal to -2. If I add 2 to both sides, I get x2 equaling plus 6x3s, which is 1, is equal to 5. So we have x1 minus 0, this just goes away, that goes to 0, plus 6, x1 plus 6 is equal to 5. subtract off the 6, and we get x1 equals -1. Okay, now our solution we're going to write as a solution vector. So that's x1. So if we were to write it as a column vector, remember we could write it like x1, x2, x3. Then if we wrote it as a column vector, we could write it as in matrix form as x1 was -1, x2 is 0, and x3 is 1. So that could be our solution column vector, column 3 vector. Okay, or I could just write it as a regular standard vector or in point notation, -1, 0, 1. Okay, and so that would be my solution. Okay, the solution to the original system of equations. And we could check that if we really wanted to. We could go back and plug in -1. I'll just write it up here. Okay, all the way back at the beginning. We could plug in -1, 0, 1 into each of these lines and see that they do in fact work. Okay, if I get -4 plus 6, because the -3 is going to go to 0, all the values in the for x2 are 0. So that middle value is always going to be 0. So is -4 plus 6 equal to 2? Yes. Is -1 plus 6 equal to 5? Yes. Is 2 plus -8 -6? Yes. So all three of the equations check out. Erase that. Okay, let's cover some more definitions here. Okay. Definition. The particular case where a matrix is matrix. The particular case where a matrix is placed into reduced row echelon form is called Gauss-Jordan elimination. So I guess Jordan took Gaussian elimination, just kind of said, hey, well, if we go to reduced row echelon form, then I can just add my name to history, and it will be the Gauss-Jordan elimination method. Okay. That's kind of one of the rules of engineering is, you can either create a product that serves a purpose, or you can steal someone else's idea and make it better. And it seems that that's what Jordan did here. He stole someone else's idea and just made it better. Theorem. Consider the m by n matrix linear system A times vector x, that's my variable matrix, is equal to vector b. Okay, let the rank of A equal R, and the rank of A star, that's my augmented matrix. Okay, so A is just my coefficient matrix, so keep that in mind. Okay, so the rank of A is R, and the rank of A star, that's my augmented matrix. That includes vector B. It's kind of A and B together, but with that augmented line. Okay, the rank of A star is equal to R star, okay, or R pound. I guess I should say A pound and R pound. Okay, where A is the coefficient matrix. And A pound, or A number sign, is the augmented matrix. Okay, let's consider that. I'm going to put a semicolon here that just says, hey, we're continuing this thought. Okay, augmented matrix 1. Okay, if R is less than R pound, the system is inconsistent, said to be inconsistent, and it has no solution. Okay, if we look at an example of this where the augmented matrix, say, is equal to 1, 1, 0, 0, 1, 0, 1, 0, 2, and then 0, 0, 0, 3. Okay. Okay, what's the rank of A? The rank of A, well, that's just the coefficient part of the augmented matrix. The rank of A is 2. And what's the rank of A pound? The rank of A pound is 3. And notice that R is less than R pound. Okay, our rank of A pound is less than the rank of A, so R is less than R pound in this case. Okay, and if that's true, then it has no solution. There's no solution to the linear system of equations. Okay, this would be like if you had two parallel lines or two skew lines in 3 dimensions. Okay, they're never going to intersect, and so there's no solution. So here 2 is less than 3, and so we say that there is no solution. Okay, okay, the second, I'll move this down a row. Let me do that. Okay, that fits better on the page. Okay, let's go to the second thought on this. The second thought is if R equals R pound, if the rank of the coefficient matrix and the rank of the augmented matrix are equal, the system is said to be consistent. Is consistent. Okay, that means that at least one solution exists. Okay, there could be one solution, there could be an infinite number of solutions. Okay, but at least one exists. At least one solution exists. Okay, if this is the case, that the rank is the same, then we have two criteria, two options for what the consistent system is. Okay. Okay, we say that the system is independent if it has exactly one solution. Independent if it has exactly one solution. Okay, that is, if R pound equals N, okay, then that would be the number of columns in A. So R is the rank, right? The rank of my augmented matrix. So if the rank of my augmented matrix is N, okay, remember A is an N by N matrix. Okay, our coefficient matrix is a square matrix. It's an N by N matrix. So if the rank stays, okay, for our augmented matrix, it stays at N. This is the number of columns in A. If R pound is equal to N, or the number, probably shouldn't use that symbol, the number of columns in A, okay, also the total number of variables, okay, it's just the total number of variables in my system, also represents the total number of variables. Okay, so let's make this more concrete. Okay, so if the total number of variables is 3, then that augmented matrix needs to have a rank of 3. Okay, we can't have a row of zeros, okay, or a row that only contains one element. Okay, only one non-zero element. It can't have that. Otherwise, we have, you know, an infinite number of solutions. We don't have just one solution. Okay, if we go back to our previous example, okay, where we did end up with one solution and it wasn't an independent system, it was consistent and independent. Okay, our augmented matrix, okay, even in row echelon form, okay, it has rank 3. It was a 3 by 3 matrix. Our coefficient matrix was a 3 by 3 matrix. And so what is our rank for our row echelon form of our matrix? Our rank is still 3. It still has 3 rows that we can work with. Okay. Okay, and if that's the case, then it is an independent system and it has exactly one solution. So maybe let's underline exactly one solution. Okay, B, if we still have R equaling, okay, the rank of the coefficient matrix and the rank of the augmented matrix are still equal, but they are less than N, okay, less than the number of columns or the number of variables I started with, then we have what's called a dependent matrix, dependent system, and it has an infinite number of solutions. Now, that doesn't mean that anything can be a solution. Okay, it means that it has a very specific solution set, but there's just an infinite number of points, infinite number of values that could satisfy that solution set. Just think of a line. A line is a very specific relationship between two values, but it does go on forever. And so there are an infinite number of solutions, but not every point in the universe is on that line. Okay, it's a very special relationship between the input variable and the output variable, between the domain and the range. Okay, so and between the x and the y, however you want to define it. Okay, so again, not an infinite number of solutions doesn't mean that everything's a solution. It means that there just happens to be more than one value for each of these variables that work. Okay, we'll get to what that means in a second here when we do our second example. Okay, so part B, the system is dependent. Okay, that means that it has, if it has, I won't say if, the system is dependent, then it has, then it has an infinite number of solutions, or I'll say infinitely many solutions. With at least one free variable. Okay, if R pound is less than N. Okay, so the rank are the same. Maybe it's rank 2, right? We say that we look at this example up here, we had rank 2, okay. Maybe we end up with a row of zeros, and we end up with, you know, something that has rank 2. Would have infinitely many solutions. Let's just show a matrix that has this behavior. Okay, so we would say that 1 0 0 1 0 1 0 2, and then a row of zeros, okay, has infinitely many solutions. Okay, here R is equal to R, if I do the augmented portion here. Okay, R is equal to R pound, which is equal to 2. Okay, but that's less than N, that's less than my original dimensions on my coefficient matrix. My coefficient matrix was 3, so obviously 2 is less than 3, and so it has infinitely many solutions. Okay. Okay, how would I represent this infinitely many solutions in this case? Okay, and what does it mean to have a free variable? Okay, well, a free variable is just a variable that can take on any value. Okay, it's exactly what it says. It's free. It's a free agent. Okay, it can take on any value it wants. It's a free variable. It's not locked in to a certain value. If we look at our first two rows here, and I were to say that the variables that I'm working with are x1, x2, and x3. Okay, and I were to write out the solution here, it would be 1x1 plus 0x2 plus 0x3 is equal to 1. Okay, and so this actually locks in what x1 is. X1 would have to be 1. Okay, the second row is the same story. So we have x x1, 0x1 plus 1x2 plus 0x3 is equal to 2. So that again locks in what x2 has to be. X2 has to be 2. But let's look at the third row here. The third row is 0x1 plus 0x2 plus 0x3 equals 0. Well, of course it does. If I zero out everything, it's going to be 0, regardless of what x1, x2, and x3 take on, what values those take on. And so what can we say about x3 here? Well, we could say that x3 could be anything. And the way that we represent the anything is with another variable. We just say that this could take on value t. Okay, and so our solution, would be 1, 2, t. Okay, to that augmented, and that's a reduced row echelon form. So that's Gauss-Jordan elimination there. Okay, let's do our second example here. Okay, determine the solution set 2. Five x1 minus 6x2 plus x3 equals 4. 2x1 minus 3x2 plus x3 equals 1. 4x1 minus 3x2 minus x3 is equal to 5. Okay, let's set up our augmented matrix. So 5, 2, 4, -6, -3, -3. Okay, and then we have 1, 1, -1, and then 4, 1, 5. Okay. Okay. So let's try to put this into row echelon form. Actually, let's just put it in reduced row, place it in reduced row echelon form. Okay. I want reduced row echelon form or just row echelon form. Well, let's go for let's just go for row echelon form first. Okay, let's see if we can do anything with that. So I'd like to get a 1 in the first row, first column position. And so in order to get a 1, I'm going to multiply row 2 by -2 and add that to row 1 and replace row 1 with that. So let's do that. Okay. So I'm going to go, oops, I'm going to go A, row 2, replacing row 1, and I'm multiplying row 2 by -2, and that should get me a 1, that desired 1 there. Okay, so multiplying row 2 by -2, I will get -4. This is going to become 6. This is going to become -2 and then -2. Okay. So I'm going to end up with adding these two rows together. I'm going to end up with row 1 being 1, 0. That's convenient. Okay, negative 1. Okay, and then 2. Okay, then I have 2, negative 3, 1, 1, 4, negative 3, negative 1, 5. Okay. Okay, the next thing that I want to do is I'd like to get a 0 where that 2 is. Okay, and so let's get a 0 here. Let's multiply our row 1 by negative 2, add that to row 2, and that should knock out that 2 and get me a 0. So let's do negative 2, 0, 2, and then negative 2 times 2 is negative 4. Okay, add that to row 2. So row 1 stays the same. So we get 1, 0, whoops. 1, 0, negative 1, 2, 0, negative 3, 2 and 1 is 3, and negative 4 and 1 is negative 3. Multiple. Okay, and then the last row just stays the same. 4, negative 3, negative 1, and 5. So what did I do there? I multiplied row 1 by negative 2 and added it to row 2. Okay. Kind of a reversal of what we did before. Okay. Yeah. Now let's work on this 4 down here. So what are we going to do? Yeah, we're just going to multiply row 1 by negative 4, add that to row 4, and that should give me another 0. Okay, so this thing is going to become A1, 3, negative 4. And we're going to get negative 4, 0, 4, and negative 8. Okay, so now add that to my third row, and we will get 1, 0, negative 1, 2, 0, negative 3, 3, negative 3, and then that's going to get me a 0, and then a negative 3, and then a positive 3, and a negative 3. And then notice that the row 2 and row 3 are identical. So if I were just to add row 2 and 3, I'd end up with a row of zeros. So let's do that. Okay. So I'm going to multiply 1 by row 2 and add it to row 3. So that just means I'm going to add straight row 1 and row 3 and replace row 3. So that is going to become 1, 0, negative 1. I'm forgetting to augment my matrices. There you go. Okay, 1, 0, negative 1, 2. And then 0, negative 3, 3, negative 3. Actually, I want to multiply the second row by negative 1 and then add, so they cancel over. So let's show that. That's just going to be 3, negative 3, and 3. If I add that together, then I get zeros across the board for the third row. So 0, 0, 0, 0. Boom. Okay. Okay, I would like to still get a 1 along the diagonal here. Okay, and so we're going to get, let's multiply the middle row through by negative 1/3. Okay, so multiply row 2 by negative 1/3, and we end up with 1, 0, negative 1, 0, 1, negative 1, 1. Okay, and then a row of zeros, 0, 0, 0, 0. And I think that that's as far as I can go because I don't have another row to be able to cancel out anything else at this point. So I think that that's as far as I can go. If I were to try to combine rows 1 and 2, I'd be kind of going backwards. And I would eliminate the zeros that I've worked so hard to get. So at this point, I'm done. I can only go to row echelon form. I cannot do complete reduced row echelon form because we have that row of zeros. Okay, that kind of answered that question for me. Okay, so what is the rank? Okay, what's the rank of R star? Well, the rank of R star, okay, is equal to 2, or R, keep saying R star, it's R pound. Okay, R pound is equal to 2. Okay, that's also what, if we did this process and we just took the coefficient matrix, we would end up with this guy here, this 3x3 matrix, okay, coefficient matrix, but it would still have a row of zeros. Okay, a complete row of zeros. And so R pound is also equal to R, which is equal to 2. And so this is a consistent yet dependent because this 2 is less than my n, which was 3. And so 2 is less than 3. Therefore, it is it doesn't have no solution. It has a solution. It just doesn't have one solution, one unique solution. It has an infinite number of solutions. So how do we deal with that? Well, let's go back to our original system. Let's take our original system, rewrite it as our new system, and then see what we can do to make sense of some of these variables. I will say that x1 plus 0x2 minus x3 is equal to 2. That's going to become x1 minus x3 equals 2. Boom, that's my first equation. Okay. And then my second equation is that 0x1 plus 1x2 minus 1x3. I could put ones in here if it helps you out. Okay, is equal to 1. What's that going to become? That's going to become x2 minus x3, okay, is equal to 1. And so what I can do is I could toss the x3 to the other side, okay, and I could say that in both equations, I could say that x1 is equal to 2 plus x3. Okay. Okay, and that x2 is equal to 1 plus x3. So we can see that we have x1 dependent on x3, and x2 is also dependent on x3. So it only makes sense to let x3 be this kind of free variable. Okay, it can take on whatever we want it to. Let x3 equal t. And so this tells me that x1 is equal to 2 plus t, and x2 is equal to 1 plus t. And so when we rewrite this, we say that the solution is x1. It'll go x1, x2, x3, but we're going to write that in terms of t. So this is going to become x1 is 2 plus t, x2 is 1 plus t, and x3 is, in fact, t. Okay, and we say this is 2 plus t, 1 plus t, and t, and where t is an element of the real numbers. Okay, we're going to restrict ourselves to the real numbers at this point in time. Okay. Although they can be complex. Okay. All of these things can be done with complex numbers as well. Okay, but for now, we're going to restrict that to the real numbers. Now, let's take note. Okay. 2 plus t, 1 plus t, and t, I could rewrite that as 0 plus t. Okay, could be rewritten as 2, 1, 0 plus t, t, t. Okay, if you were to write these kind of as vectors, as vector addition, we get 2, 1, 0 plus t, t, t. We could factor out that t, and we get 2, 1, 0 plus t times 1, 1, 1. Okay, where once again, t is an element of our real numbers. Okay, and so we could write it like that as well. Okay. Okay, that's section 2.5. I'll see you in the next section.